Good morning. Starting trig. So before we can study the trigonometric functions, we need to study angles. A lot of this might be reviewed from geometry, from high school geometry. Ray consists of one point on a line and all points extending in one direction from that point. This would be a ray. Angle is just the union of two rays having a common endpoint. This is called the vertex. Two rays are called your sides. Right. Typically define angles with 3 points, with your vertex being the middle point. And so the angle BEF. Or we'll just simply label it as such. Conventionally, for angles, we use Greek letters. Most common two, theta, which is what's up there, and phi, which we will see later. Creating an angle. Start with the two rays lying on top of one another. You fix one ray. You rotate the other ray. We call the fixed ray the initial side, then the ray that rotates is your terminal side. Measure an angle is just the amount of rotation from the initial side to the terminal side. And there are two commonly used units of measure. First is the degree. It's defined as 1/360th of a circle rotation. And then there's also the radian, defined to be 180 over pi degrees. It's 360 degrees, circle. One full revolution on a circle is 2 pi radians. Angle is in standard position if its vertex is located at the origin and its initial side is the positive x-axis. An angle that is measured counterclockwise is positive. Angle that is measured clockwise is negative. So in terms of rotations, counterclockwise is the positive direction. Triangles are coterminal if they have the same terminal side when drawn in standard position. And an angle's reference is the size of the smallest acute angle formed by the terminal side of the angle and the horizontal axis. What is an acute angle? Remember that from geometry.
An angle that's less than 90 degrees.
That's half of it. Is negative 10 degrees acute?
No.
So what's the other half?
It has to be positive.
Between 0 and 90.
But not 90.
Hmm?
But not 90.
No, 90 is a right angle. Or radian 0 and pi over 2. Brings up a good point. Unless it's otherwise specified, angle measures are always in radians. Right, so arc length is defined to be the length of the curve along a specific arc. We consider a circle of radius r the length of the arc that is subtended by an angle theta, which must be measured in radians, is r times theta, the radius times the angle. And the sector subtended by an angle theta, again, has to be measured in radians. It's a half r squared theta. So let's set all the angles coterminal with 40 degrees. Remember, coterminal angles have the same terminal side.
Would it be like adding 180 or not? Adding 180 to it
40 degrees.
is in the first sector, first.
Let's try and be precise.
that.
Let's just say it's 40 degrees.
Mm, 220.
220 would not be coterminal. So we've already rotated it this way, right, 40 degrees. To be coterminal, when you rotate, you have to end up at the same terminal side.
Oh, out of 360.
Well, one full rotation would be 360 degrees.
Yes.
That'd be coterminal.
Oh, so 360 plus.
But if I do another 360, it'd still be coterminal.
So
Another 360. Or
opposite. Negative.
go clockwise. Right. So it's actually any multiple of 360 degrees.
Mm.
I want to call it coterminal angle.
So it'd be like 400.
Right. So listing out every coterminal angle is not possible because there's an infinite number of them. But we describe what they would be.
All real terminal.
And so it's just saying it's a set of all angles of the form 40 degrees plus a multiple of 360 degrees. And obviously an angle would be coterminal with itself. So 40 degrees is listed in that set. These would be all your coterminal angles.
Oh, and 2 pi on both of them.
Not just 2 pi.
Negative 2 pi as well.
Once again, any multiple.
Like 2 pi.
2 pi.
That's what I mean, but I don't know how to write that. Like it would be like 2 pi.
I'm just going to start by drawing the angle. No, 60. 120. That'll be 2 pi over 3 in standard position. And again, it's the same argument as before, except now we're in radians instead of degrees. So coterminal angles to 2 pi over 3 would have the form 2 pi over 3 plus a multiple of 2 pi.
Two n pi?
Yeah. N is any integer. reference angles. Unlike coterminal angles, which there are an infinite number of them, each angle has only one reference angle.
Is that the,
So that is what we're going to have to try and figure out. So reference angle, by definition, the smallest acute angle that the terminal sides makes with horizontal.
alright, so that would be just minus 360.
Where do you have to subtract 360?
Let's subtract the,
What would you get?
120.
Is that acute?
Yeah.
So that's not a reference.
so you just
The
have.
first thing we're going to do is draw this in standard form. The problem is you're going to actually need to know what the reference angle is to do that. So instead of actually being precise, I'll just do it this way. And if you look at the coterminal, yeah, 120, that is going to
That's
be.
gonna be just the opposite side of it, right?
Why are you doing a triangle? I have no idea. Right, that'd be pied out 120 degrees. But we went more than one rotation, right? So we represent it that way. That's the angle we want. That would be its reference angle.
That would be 120 minus 180, so that would be 60 degrees.
Other way around.
Negative 6.
Negative 60.
180 minus 120.
So it's negative 60. Or 60 degrees.
60 degrees. Reference angle 60 degrees. Three pi over 4. That angle. I should technically be drawing arrows to represent a direction that we're rotating, but we typically never do.
I always get so confused when it's in like radians and stuff. Do you have like any advice like on how like?
Other than being able to quickly convert it in your head.
Yeah, like how do you, because I learned in physics, but like I forgot like how do you?
Well, we will be doing conversions.
Oh, okay.
That's the angle we're looking for.
1.5, negative 1.5.
So remember, it has to be acute, so it has to be between 0 and pi over 2.
Oh, that's what I'm 1.5 over 4. That's what I said.
Pi over 4. The way to do it, algebraically? Yeah, let's go with that.
Because that would,
You first try to find its coterminal angle. Right, so instead of measuring it this way, you want to measure it this way. So what is that coterminal angle? We just add 2 pi to it, it's 5 pi over 4. That would just be 5 pi over 4 minus the pi. That gets you your pi over 4. Right, because you know that straight line is pi, 180 degrees. And you went a little further beyond that. Both of these concepts are going to be really important. Finding coterminal and reference angles. It's generally the easiest way to work with trig. So now converting between measures. 5 radians written in 2 degrees. I'll start with writing 5. Now here's a little nuance. Radians, not actually a unit. So when we're talking about angles, if we write 5, that's implied to be measured in radians. So the radian itself is a unitless measure. But by the definition of a radian was what, 180 over pi degrees? So you just multiply it by its conversion factor of 180 degrees over pi.
and then you just flip it to do it.
So
right.
the conversion factor is this. Pi radians equals 180 degrees. That's your conversion factor. You just have to decide what is the appropriate one to use, 180 degrees over pi or pi over 180 degrees, based on the problem. In this case, we want degrees, so it's 180 degrees divided by pi. What's 5 times 180?
900.
So it's 900 over pi degrees. And leave it like that.
If you were to divide by pi, that would be the degrees, no?
No, I am dividing by pi.
But you don't want that angle?
That is the angle. 900 over pi degrees, that's the angle.
You simplify it?
That is simplified.
Like you don't
You're thinking of approximation.
you don't
No,
want
you do not approximate.
280 like 700?
You do not approximate.
What does that mean?
Put it in decimal form. So you leave it like that. The only time you approximate is if you're told to or there's already a decimal given to you. Yes. This notation known as DMS notation. Or D, or degree, minute, second notation. We already know what a degree is, so don't need to worry about that. Minute, called arc minutes, but we just simplified as minutes. That is the single prime. So 1 arc minute is defined to be 1/60th of a degree. So you have 60 arc minutes in 1 degree. Arc second. Is 1/60th of an arc minute. So you have 60 arc seconds in an arc minute. Which means there's 3,600 arc seconds in a degree. Easy way to remember this is it works precisely as hours, minutes, seconds. Degree would be an hour.
Is it divided by 60/60?
So 60 seconds in a minute, 60 minutes in an hour. 3,600 seconds in an hour. It behaves the exact same way as time in that regard.
So you got 424 hours. You divide that by 60.
Well, first we have to convert this to radians. So here's what we're going to do. We have to convert this to radians. So first, just write this as purely degrees. And that's going to be fine. Again, nothing to do with the 424 degrees, that's already in degrees. 34 arc minutes is 34/60ths of a degree. And then 24 arc seconds, 24/3600ths of a degree. Now write that as a single fraction.
Are you getting that? Because it's like 60 times 60 equals 3,600.
You have 60 seconds in a minute and 60 minutes in an hour. So how many seconds in an hour? There's 60 times 60 of them. (31,843/75ths of a degree. Or I guess 31,843/75ths degrees. That's larger than 1. Oh, we're not done. That's just finally writing that in degree. We now want that in radians. Right, well, your conversion factor, pi equals 180 degrees. So we use pi over 180 degrees. I'm pretty sure there's no common factor between 31,843 and 180.
I'm still confused how you get 31,843.
Single fraction. So you need a common denominator. So all I did was I added these fractions.
And so like 424, is there like a zero there then?
1. Remember, it's always understood to be over 1. So LCD here happens to be 75.
Okay, LCD at the top is,
So the LCD, you want the LCD between 3,600 and 60. Your least common denominator. Actually, I don't think it is 75. It just winds up simplifying down to 75. The easiest thing to do is just use 3,600 as your common denominator. It's not the least common, but it is a common. Then it's just 34 times 60 and 424 times 3,600. Add them all together and then simplify at the end. Of course, it'd be easier just to use your calculator for that. Your calculator also has the option to convert between DMS and regular degrees, but it's not entirely accurate, so be careful using that. Okay, those would be our ratings. The DMS isn't really used that much anymore. It's really not used that often. It's only really ever used if you need really precise measurements. So you're probably not going to see DNS a lot. It's more along these lines, these kinds of angles that we're going to be dealing with. 30 degrees.
gradient pi over 180.
580 degrees. So that's the conversion factor we're multiplying by.
And there's a 1 under there, right? Like that.
What's 30 divided by 180?
Six.
No, 1/6. So pi over 6. 30 degrees, pi over 6 radians. That might be one you want to memorize. I'd say there's probably 4 you'd want to know.
30, 60, 90.
30, 45, 60, 90.
30, 45, 60, 90.
I guess technically 0, but 0 is easy. 0 degrees, 0 radians. Mm-hmm. 135 degrees. Again, we're going from degree to radian, so the conversion factor pi over 180 degrees. 135 over 180. No, they're both divisible by 9, so that's a start. There's 135 over 9. I think it's 15. Fifteen's the only one that would make sense. That's the only one that would give you 5 at the end. So that's 15 over 20. 3 over 4. So 3 pi over 4 radians. And back into the DMS. This one's actually pretty nice. "25 degrees and 30 arc minutes." "30 arc minutes is half a degree. How much is 51 halves?
Oh, wait, by half a degree, you mean half of 1 degree?
Mm-hmm. And 1 degree is 60 arc minutes. So 30 arc minutes have to be half of a degree.
How'd you get 51?
2 times 25 plus 1. Common denominators.
Gotcha.
Now times pi over 180 degrees. Both 51 and 180 are divisible by 3. 51 over 3. 17. Pi over 180 divided by 3, 60 times 2 is 120. 17 pi over 120 radians.
Would that be the same as doing 51 divided by 2 over 180?
Mm-hmm.
Because in the calculator it says 17 over 60. So it would be 17 pi over 60?
Should be 17 over 120. That is the correct answer. Check the way you typed it into your calculator. So the other way to look at it is it's 51 over 360,
Yeah.
which would simplify to 17 over 120. Again, first thing you want to do is write this just in degrees. 24 arc minutes, 24/60ths of a degree, 35 arc seconds, 35 3600ths of a degree. And at this point, your best bet would just be to try to plug that into a calculator. Six 6,107 over 144 degrees. And now multiply by your conversion factor. Sadly, 6107 has nothing in common with either 144 nor 180. $144 times 180, 25,920. Now, what if you are given it as a decimal?
You just do the same thing with pi over.
This is where now rounding rules come into play. Because this is obviously going to be an approximation. Right, so we are going to multiply by pi over 180.
But now you're going to go the full way. And pi is 3.14, right? No.
I will never use 3.14 for pi.
This is 3.1415. And
It keeps going. So I just use the pi button on the calculator. That's always your best bet.
so you just plug all that in, basically.
Yeah. There's actually two ways we could write this. So one, this screen keeps changing on me. Like I said, there are two ways to do this. The first way is to keep it in terms of pi. So you just write 165.7 over 180. But how many digits do we want?
Two.
Are you familiar with the term significant digits, significant figures?
No.
But I never understood that, though. I really didn't understand that. Like, we're not, professors explain that.
So there are a lot of roles with sig figs.
I understand it in, engineering, but, when it comes to, physics and stuff, it was completely
Well, it's the same thing. Sig figs are sig figs regardless of the science.
But in, engineering stuff, we really only do, 3.
Then you're not dealing. Then engineering is not dealing with sig figs. You might be dealing with decimals.
It was engineering of features, stuff like that. But I never understood it.
We have in this problem 4 sig figs. So the rules for sig figs a digit is considered significant. In this case, all four of those digits are significant, as long as it's not a leading zero or an ending zero.
So if it was 0.0205,
Again, this is where the rules get.
that would be
Very.
three significant.
That is actually three significant digits.
Oh, because you have to count this.
Because what this is saying is we're confident that it's 0.025 up to that digit.
Okay. But
So this zero actually is significant because it's after a decimal.
Yeah.
This zero isn't.
Mhm.
And neither would any of those.
But if it was 0.0025,
By the way,
or significant.
These are now significant. So actually, you misspoke it. Ending zeros are significant, not leading zeros, unless that leading zero comes after a decimal. Because now, if I write out this far, just get rid of those. What this is saying is that we are confident in this measure up to that digit.
That's why the repeating thing is.
However,
That's 4.
that's one. Those zeros are not considered to be significant. Unless
That's why I got like a.
I do this. Now the decimal place, now that's 4 sig figs.
And if it was 1,000 point, like 1.
Now- Zero, that's now 5 sig figs.
Because it's coming after.
Just comes after that decimal. So without the decimal place, we can only say we're positive up to the 1,000th unit. If I put a decimal there, I'm now saying, well, now I'm confident up to the units. Now I'm confident up to the tenths, up to the hundredths, so on and so forth. So the significant digit is really just a measure of confidence in the measurement. It's weird.
You explain that a little better than you.
But when you work in science a lot, it becomes very clear. You start to, I don't want to say clear, let's say, but the rules, you kind of now just understand them.
So in the part we're doing it would only be 0.9205.
I'll get back to that. So that's the rules for significant figures. Now I'm dealing with operations of significant figures. When you multiply, your answer has the same number of sig figs as the lowest number of sig figs that appears in your operation. In this case, pi of 180 degrees is an exact measurement, right? It's a conversion factor, so we just ignore that. That has an infinite number of sig figs.
So that has 4.
That has 4, so that's our lowest number. So our answer, because it's multiplication, needs to have 4 sig figs.
Okay, so
When you add, you keep the number of decimal places as the fewest number of decimal places in the operation. So that ignores sig figs. Adding ignores sig figs. That's strictly decimal places. Multiplying is sig figs. All right, so we come up. Let's go back to the calculator. We need 4 sig figs.
0.9205.
1, 2, 3, 4. But this is going to round.
To 6.
So now you have a rounding rule. Depends on the convention you use.
1, 2, 6. 5, 6.
Right, so one of the most used conventions is you go to the next digit, 5 and above round up, which would be 6. Below 5, you keep it as 5. There's another convention. Convention that I used a lot was, if it's below 5, you keep it. If it's above 5, it rounds up. If it is 5, you have to look at the next one. And the next one. The next one.
You gotta keep all.
Because at exactly 5, that's halfway. At halfway, you round up or down, because it's exactly halfway. Without depend on your next digit. But again, so the problem with this here is that I'm not entirely sure if this 5 is, if this is actually 5 repeating,
Yeah.
or if at some point it does change. Right? But the calculator can only go up to a certain precision. For this class, I'm just going to stick with the convention of 5 and above, round up. So just round that up to 06. It'd be 0.9206.
That's just the first way of doing it, because then you could just plug the whole thing in and you get like 2.84 and then you just put a radius.
Right, so this is if you, I did this. This is if you wanted to keep it in terms of pi, which some problems are going to require you to do.
But like you said, radius doesn't have a radius.
No, it's not a unit, but you're still keeping it in terms of pi, right? You're leaving pi alone. Right, so you're not estimating this with respect to pi, it's just, you leave pi as a number, and it's times 0.9206. The other way is, yes, if you want to, because it is a true, if it's a true approximation,
2 times the pi.
then you then multiply by pi, and then do the sig figs that way again. Now again, the reason you don't want to use 3.14, that's 3 sig figs, which changes this. If you just type it into your calculator, so I'm going to just do this to show off. That's the precision. Oh, again, switch screens, that'd be nice. This is the precision that my model calculator, the T9 Inspire CX2 is going to go out to. And I think your, the 84 will also go out this far. that's 12 sig figs, which for this course is more than enough. For some more advanced sciences, that actually may not be enough. You may need to go out even further, in which case you're going to have to use a more powerful computer, which means more powerful calculator, which means a computer. But this is why we want to use the pi symbol itself, because it goes out to 12 sig figs.
Yeah, because when you do that, it turns into 2.89201. So with that,
So what I'm going to do is I'm going to do this. As a general rule of thumb as well, you never round your answers until the very end. Right? Because the more you round throughout a calculation, the more error you accumulate. So instead of doing the 0.9206 times pi, I'm going to put it in the original way. 165.7 divided by 180, then times that by pi. That's going to give you the most precise answer with the lowest error. But we still want 4 sig figs.
only 4?
Right? Again,
Oh, yeah.
this only has 4 sig figs, so I can only be confident in my answer to 4 sig figs.
So it would just be the 2.
2.892. Now, again, I technically actually here shouldn't be using equals.
You put the little squiggly lines?
Right? These should be approximations. Not that huge of a stickler. Right, so either of those two answers would be acceptable to me, unless the problem specifies keep it in terms of pi. Or if I actually say approximate. If I say approximate, then I want the 2.892. If I say keep it in terms of pi, it's that first one, right? 0.9206 pi. If it doesn't say either of those, and there's a decimal, you know it's going to be an approximation, you can do either one. And as a general rule of thumb, if it just gives, so if it's just like this, you have to use the sig fig rules. If the problem tells you how many decimal places to use, then you go with that. Or if it tells you how to approximate, you use that. I think for the most part I do tend to, if it is an approximation problem, I'll tell you the decimal places I want. Especially on a quiz when it's a numerical enter answer. I'll tell you exactly how much I want because that's the answer that I'm going to put in. Again, times pi over 180. I'm only going to do one of them. Now I'm going to say this is an approximation. So make it 3.85 times pi over 180. I'm sorry, I did that backwards. It's times 180 over pi, right?
No,
I was right. I'm looking at the wrong problem now. Oh dear.
so it'd only be 3 digits.
How many sig figs do we want?
3. So you do the 0.0, or do you just do the 0.067? Because like usually to make it look better, you keep that 0 in front, right?
I typically do.
But then would you just
Actually-
do 0.06 or 0.7?
See, now that I actually look at this, I just clicked the wrong button. Where was I? Here I am. I was right the first time. Leading zeros aren't significant. This isn't significant. So go out to here. Right, so your first significant digit will start here. And all of these. Yes, I get it. Push the wrong button. There we go. So I come back out to here. So if I load this back up, 3 sig figs, right, and then negative 3.85, and that's the low because the pi over 180 is it's a conversion factor of an exact measurement. So our answer needs to have 3 sig figs. 1, 2, 3. And that's a 9, so that will round up to 2. And then how you write it, whether you include this 0 or not, that's entirely up to you. Right, you can either do negative 0.0672 or negative 0.0672. They're the same thing. I tend to just write the 0 before a decimal. don't know why, I just always thought that looked nicer. Oh, I skipped those, that's right. Sake of time, let's look at some radians to degrees. Again, this is another important angle to remember. And then the conversion factor, 180 degrees over pi radians. $60 degrees. Pi over 9 in terms of degrees. Pi's cancel out, right? 180 over 9 is what? What's 18 over 11?
20?
It's 20.
Oh.
Times 5. 100 degrees. Two-fifths of a radian. I should probably fix that. That shouldn't be plural. Converted factor is still 180 degrees over pi.
$22.9.
We're not going to use a decimal.
Do you round it? 22?
We don't do approximations here. Because there's no decimals, 2/5 is an exact value. So you don't want to type in the pi in the calculator. 180 divided by 5, that is divisible by 5. 40 would be 200, right? So that's going to be 36. And then 36 times 2 is 72. So it'd be 72 over pi degrees. And 4/5 4/3 radians. Same conversion. 180/3, that's very simple to do. What's 180/3? What's 60 times 4?
240.
240/pi degrees. So the one that is going to require approximations. 1.53 radians. Again, they already gave us a decimal, so this is definitely an approximation. .53 times 180 degrees over pi. Not 1 equals, I'm going to do approximation. Again, there are two ways you could represent this. If you want to keep it in terms of pi, I'll do that one first.
That would be 270.
How many sig figs do we want?
3. So 275 pi degrees.
Not pi,
So I thought you said you were going to keep it in
over pi.
over. Okay.
Or true approximation,
And 87.7 degrees.
87.7 degrees. So again, I know those two answers. We'll have more practice converting with these types of problems. Arc lengths and sector areas. I'm going to cheat. So I don't have to draw a perfect circle, I'm just going to use technology to do it for me.
You could do it like the arc minutes.
12, that's 12 and 6 on the clock. What's 360 over 12?
$360.
30 there, right? So each of the minute symbols, right, the 12, 1, 2, 3, occur at multiples of 30 degrees. That'd be our clock.
I mean,
So they say the minute hand is 12 centimeters long.
so that's going to be the radius.
How far does the tip of the hand move during 20 minutes? Well, 20 minutes would go out to what?
20 over 60. 20 minutes would be,
Go out to that 4, wouldn't it?
yeah. And we're saying that it started at.
I'm going to say it's going to start, it doesn't matter where it starts. The argument's the same, but I'm going to have to start at the 12. So the arc we want to find right, we want to find that length. Everyone's good enough. That one work. All right, that's the length we're looking for there. What's that angle? And remember, we want it in radians.
Do you don't do 2 pi r and then do 20 over 60?
I mean, you might be able to do 20,
20 over 60 is the hour, or the minute divided by hour, and then the 2 pi r would be the 2 pi times 12.
I would ignore that. Because we just said each of these ticks represents what? 20 degrees, or 30 degrees rather.
Yeah.
So that's 120? What's 120 degrees in radians?
Oh.
2 pi over 3. Arc length is radius times the angle measured in radians. 12 centimeters times the 2 pi over 3. Over 3 is 4 times 2 pi, 8 pi centimeters. That is the distance that the tip of the minute hand traverses in 20 minutes. And it doesn't matter, like I said, where you start, where the minute hand starts, because it's still going 20 minutes, which means it's still going to subtend an angle of 2 pi over 3 in 20 minutes. Central angle of a circle radius 30 intercepts an arc of 6 centimeters. Express the angle in both radians and degrees. And so again, it doesn't matter where I draw my 2 rays. That's irrelevant. So the easiest is just to start like this. But that's not kind of like right in the middle. That should be good.
That's 30.
Right, and we need to find theta. How I draw my next angle doesn't matter. Just going to do that. We know that the radius is 30 centimeters. We know that this length here is 6 centimeters. That is what we want to find. So again, start with S equals R theta. We have S, we have R, we want to find theta. How would you find theta from this?
S divided by R.
S was 6 centimeters, R was 30 centimeters. What is that? What's 6 over 30?
1/5. That's it.
That's a fifth of a radian. Right, so that would be the measure in radians.
Then you convert it.
Now convert that to degrees. Which is what? A fifth times 180 degrees over pi. What's 180 over 5? That's 16.
Yes.
Yeah, 16. (16 over pi degrees). So that's the angle that's subtended.
And 180 over 5 is 36.
Yeah, you're right. Thirty-six over pi degrees.
That's what I thought too, but I didn't want to question.
Mhm.
Sometimes you're like smarter than the calculator.
Well, calculator is only as smart as its user.
Mm-hmm.
You'll be smarter than or,
It's a common saying in math. I can tell you how to do arithmetic, but I can't do it myself. Because mathematicians really don't ever do arithmetic, but we know how to do it.
Why?
We can explain how it's done because that's what math is. Math doesn't care about the actual process itself. It cares about explaining the process. I mean, again, it's a joke, but it kind of explains the difference perfectly. How can you tell the difference between an engineer, a physicist, and a mathematician? Put them in a room, set it on fire. The engineer will put out the fire, but the room will be completely drenched. It will be flooded. The physicist will calculate the exact amount of work required to put it out. Mathematician will have writing all over the walls, the floor, the ceiling.
and have no solution.
Walk out of the room and go, this fire can be put out. And leave. Right? We just care about describing it, proving it. We don't care about the actual process itself, actually doing it. So that's why we can explain how to do arithmetic, but we can't actually do it ourselves because we don't care.
And the engineers.
Engineers just want the money, so they just do it in the most efficient way. And the most efficient way to put out fire is just use more water than you need. Actually, here I don't. I'm going to still use the circle. Whether a curve is to be laid out on a circle, what radius should be used if the track is to change direction by 25 degrees in a distance of 120 meters? And again, how we start doesn't matter. I'm already at 45 degrees, so I'm just going to leave it there. If I want to be exact, 45 and 25 is 70, right? So I'm just going to make this now 70 degrees. Okay, well that was 25, or that was 45, so I just need to go another 25. So there. I'll set that up as my subtend. So we know we want to cover the ground at 25 degrees, and this has to be 120 meters. We want the radius. And again, start with S equals R theta. We want radius.
So it would be theta over R, or S over theta.
But what's the condition on theta?
25. Oh, it's in radians?
Has to be in radians.
Can you convert 25 into radians though? You can.
Yeah, the best way to do that is just do it right in the problem.
Mhm.
$25 over 180. They definitely have a 5 in common. I think that's, is that all we have in common? 180 is not a multiple of 25, is it? No, can't be. So they only have a 5 in common. So it's going to be 5 pi over something. I think we did that already, right? 36?
36.
Ah, yes, but 120 and 5 are also going to have a common. So 120 divided by 5, 24. 24 times 36 is going to be the answer. And then over pi.
Wait, what was the time? 32?
24 times 36.
Times 36.
2 pi over 3,
For what?
120 divided by 5 divided by 36.
Well, it's not 120 divided by pi divided by 36. 120 divided by 5 pi over 36. 120 over 5, though, is just 24. Remember, when you multiply fractions, or when you divide fractions, you flip the denominator. So that would be 120 times 36 over 5 pi. That's what I said, just what's 24 times 36?
864.
And then divide that by pi, that's the answer. And the units are meters. That would have to be the radius.
You said that, like, that's simplified already, right? You don't put it.
That's fully simplified. Right, so there's a difference between simplified and approximated.
Yeah.
Right? That is simplified. That is not an approximation, though. Circle has, or sector of a circle, has a central angle of 50 degrees. Let's draw that out first. Need this to go down to 40. Oh, it actually looks like a decent slice of pizza. That's for you, and the rest is for me. That's how it works. So we know this is 50 degrees. We want this is where it's going to get a little challenging to write on here.
And the whole thing is
The area, the sector has an area of 605 square centimeters.
I thought that
We want the radius.
the area
Area of a sector, a half, r squared theta. This would make r squared 2a over theta, because remember we want to solve for the radius. And so what's r?
would be r equals square root of 2a over theta.
Why?
Because you need to get rid of this square root every time.
So why is it only the positive square root?
Because we're talking about degrees and radians. Because a radius can't be negative.
Radius is a length measure. Length is never negative. So that's why you only take the positive square root. So there's the formula for the radius that we're going to use. And again, what was the condition on theta?
It's radians.
Has to be in radians.
So it's going to be 50 times 1 pi over
Pi over 180. Yeah, I'm too lazy. Six oh five divided by
So it would be pi over 30. It would be
oh, that's right. I don't want the pi in there.
you don't need to square that either, right? You don't need to square the 605, right? It's just 2 times 605.
Yeah, you don't need the 605 isn't being squared.
That's just a unit.
The centimeters, the area is in square centimeters. All right, so I can't type the pi in my calculator. So we'll do it this way.
So it'd be
Can I do that square root? Yes, I can. Okay.
So it would be 1,210 divided by pi over 36.
Pi is in the denominator, right? (66) over the square root of pi centimeters. Right, again, we can't give an approximation. It's not asking for one, and they don't give us any decimals. Everything's exact.
I think it's 66. Because I did the 2 times the 605 first, and I got 1,210. And then
Times that by 180. And then divide by 50. Because remember that 180 is in the denominator, which means it moves up to the numerator. Right? So you flip the denominator and then multiply. So 2 times 605 times 180, all over 5. Or, sorry, all over 50.
times 180 divided by 50.
So here's how I typed it in. Let me go to the calculator.
Oh, you did.
Right, so I just did this. Just like that. And then hit enter.
Okay.
And then I took the square root to see if that was an exact square root, which it was 66.
And then you left the.
Yeah, I left the pi out of it because then it would give you an approximation, which you don't want.
Okay.
And I just threw the pi back in at the very end. All right, and since the pi was, I'm only going to change my screen. Right, since the pi was both underscored and in the denominator. I know it's in the denominator, underscored, so that's how I know it's over root pi. Because this would stay in the denominator, right? It's not like it's down here, so it flip up. This section, I believe, in your textbook also has stuff on angular motion. So angular position, angular velocity, angular speed. Just read through that. I know I didn't include it on the homework, and I know I'm not including it on any quizzes or exams, because that can get really complicated really quickly. So I'll just leave that for a physics course. Intro mechanics, you'll cover angular stuff. And don't forget, your second exam is coming up on the 7th. Who was not here last class? Everyone else have a great day.
You as well.